Social media. It's something we use every day and it's become a pervasive part of our lives. We use Facebook, Snapchat, Instagram, and many others to communicate how we're feeling and post updates about what we're doing, and we stay in contact with those closest to us and maybe even far away from us. And we've been using social media as a tool for so long. But what if I told you that cancer cells have been doing the exact same thing? So our lab studies this structure known as a tunneling nanotube. And basically what it is it's this actin-based thin protrusion that connects cell to cell. And for whatever reason, it's upregulated in cancer cells. And basically these are membrane protrusions, so you can kind of think of it as the membrane squeezing a little bit and pinching itself a little bit, and that's what's creating this thin, long protrusion. And usually these are very thin, I mean nanometers in width, and usually can be from 100 to 500 microns in length. So that's usually a general idea of what this nanotube's physical characteristics are. But molecularly, they've been known to do a bunch of different things. For one, they've been shown to transport various cargo such as mitochondria and even genetic material. And this is really fascinating because it kind of shows that cancer cells under certain levels of stress will kind of use these nanotubes as a novel form of long distance communication. So there are lots of other different communication signals that cancer in general uses. So gap junctions are one. That's kind of a close distance talking that cancer cells use. But another would be paracrine signaling with growth factors or other hormones. But this is kind of a physical entity, this tunneling nanotube, and it's a long distance thing. And our lab has also shown in the past that they like to grow under certain conditions, so hypoxia. And hypoxia is interesting because the tumor microenvironment often is low oxygen to begin with. So the fact that these nanotubes also grow in hypoxic conditions the best is kind of interesting. Another point to note is when you have a lot of glucose, a lot of sugar in your medium, that is definitely an indicator that you're going to get a lot of nanotubes, which is also interesting because when you feed a lot of those cells with the right nutrients, then that's when you're going to get a lot of growth, so that makes sense. And that's why you also get a lot of crosstalk with those cells as well. But really this year, what we're focusing on is kind of an intersection of physics and biology with this medical device known as a tumor treating field. And basically what this tumor treating field does is it uses an alternating electric field to disrupt mitosis. And the way it does that is it forces microtubule subunits, which have a distinct polarity, to align along the electric field and stop them from aligning and proliferating, I guess. And so these microtubule subunits, or polymerize is a better way to put it. So these microtubule subunits, they can't polymerize when they are forced to align along the electric field. And actin subunits act in a similar way in that they have polarity. So we hypothesize that if we exposed cancer cells that normally form a good amount of nanotubes to these alternating electric fields, then they would also be forced to align along the electric field and prevent them from polymerization. And thus we would expect to see fewer nanotubes in cells that we expose to the TT fields treatment. And so that's kind of the focus of the lab. And quantitatively, we're also looking to measure, okay, what is the actual difference in actin polymerization versus a control? And we're trying to look at that in real time as well. So we're trying to look at both over a 3-day period, what is the difference in nanotube formation, and also in real time, what is the difference in actin polymerization between those two groups. Between a control group that doesn't get any tumor treating fields treatment and one that does continuously at different intensities. And so that's kind of the focus of our lab is to figure out what differences, if any, there are in nanotube formation based on this medical device's treatment. And hopefully from this we can confirm that actin plays a pretty big role in the structure of nanotubes. But although we would be figuring that out, hopefully, we still don't know a few things. We don't know the mechanism of how nanotubes form, and we don't know why specifically they're upregulated in cancer cells. These are kind of the big questions that still need to be answered. But I'm hoping to tackle that first problem of nanotube formation with TT fields for now.